All right, so for our last couple of reactions here, the first way to look at is something called dihydroxylation, right? And as the name implies, we're adding two hydroxy groups, right, to our alkene, right? And you can see here that this is syn addition, right? They're adding to the same side of the double bond. And we do this through one of two ways. You can see over here, right, we can do it in two steps where we have, in this case, another metal that we're dealing with, osmium 04, and an ether as a solvent, right? So something like diethyl ether, for example, right? Any ether, and then this reducing agent over here, sodium sulfate. Or we could use, again, another metal, manganese, KMnO4, water, and then sodium hydroxide, okay? And again, this is another case where the mechanism is kind of complicated, but just to kind of show you how the process goes and why it's syn addition, right, to add these two hydroxy groups, we'll take a look at the osmium mechanism here, okay? And so what's happening, again, using our sort of flat alkene here, with the bonds pointing towards us and away from us, what ends up happening is the osmium compound, right, osmium 04, adds to the alkene like this, where the alkene attacks the oxygen, double bond breaks onto the metal, and then the double bond from the osmium to the other oxygen over here ends up attacking the other site of that alkene. And so we end up forming something like this, where we have this sort of osmium intermediate like this. And this is called a osmate ester. And so what ends up happening after this, essentially, and I won't go into all the details, but we end up seeing these sort of bonds breaking from the osmium atom, mostly through the reducing agent, right, that we have up here. And our final compound, as you can see, right, is this diol, right, our two alcohol groups on our alkene, right? And again, this comes from the osmium adding to the same side of the alkene, and then when it breaks, right, the alcohols stay on the same side, right? So we get this, again, syn addition of two alcohols, as opposed to, right from the last video we saw, with the epoxide opening, that was anti-addition. This one is syn addition. Okay, so that's kind of the big key here, is that if you want to do syn addition of two alcohols, use dihydroxylation, and if you want anti-addition of two alcohols, use that epoxide acid catalyzed ring opening. So for the last reaction we'll cover here is something called ozonolysis, right? Ozone, O3. So, in essence, what ozonolysis is doing is actually breaking apart the alkene. And we'll see that here in just a second. And there's two ways to do that. Right? We can either use, right, O3, ozonolysis, followed by, in this case, methyl or sulfide, dimethyl sulfide, or we can use, again, O3 methanol, with this time a peroxide and sodium hydroxide. So the products for this are going to be different. And I'll explain what the difference is in just a second here. But to show you the mechanism of what this is going to look like, it's going to be something like this, where see ozone is going to attack one side of the alkene, and the other side will attack the oxygen, right? And the double bond will break onto our O plus middle oxygen here. And so what we end up forming is the following. Sort of tri-oxygen intermediate, which is called molazide. And again, I won't go through the mechanism for this because it's kind of complicated, but there is a spontaneous rearrangement that takes place, and we end up forming this compound, where the oxygen, one of the oxygens in the ring, ends up forming down below. Again, there's a mechanism for this, but it is kind of lengthy, so I'm not going to go over it. But this is the ozonide intermediate. Okay, so then what happens after this, right? Essentially, what ends up happening is our ozonide ends up breaking, quote unquote, in half. So there's two ways this can go, right? So we see here already, right, we've used our O3, right, in that first step, right? If we want to put it here, right, O3, and then methanol, which is just a solvent. And then for our next step, right, we could have either used, right, the peroxide and sodium hydroxide, or that dimethyl sulfide, right? So there's going to be a difference in what products form based on what we use. So if we used the dimethyl sulfide, and if we use the sodium hydroxide, what happens? And essentially, the ozonide ends up kind of, quote unquote, splitting down the middle, right? And you can see here, I didn't draw on the hydrogen, but I'll do that now. You end up forming, if you use the dimethyl sulfide, you end up forming a ketone and the resulting aldehyde. Right, you see that? We split it down the middle. The ketone is here on the left, right, with this oxygen here, and the aldehyde is here on the right. See that with the hydrogen and the methyl group here. And if we use the hydrogen peroxide, we still end up forming the ketone, but the aldehyde ends up getting oxidized to the carboxylic acid. Right? And that's the only difference between these two methods, is that with the dimethyl sulfide, you form the aldehyde and ketone, and with the hydrogen peroxide, you end up forming the carboxylic acid and ketone. Okay, the aldehyde, of course, transforming into the carboxylic acid. Again, the mechanism for this is sort of beyond the scope of what we're kind of dealing with here, so we won't worry about it. But this is essentially what's happening, right? And I've kind of clued us in down below to that as well, that we have a group with a double bond, right, using this sulfur reagent, we form the ketone aldehyde, and when we have hydrogen peroxide and the sodium hydroxide, we form the ketone and carboxylic acid. Okay, and as you can probably imagine, there's a lot of clever ways we can use this with double bonds in order to form different ketones and aldehydes. But in essence, this is sort of what's taking place. And again, your book goes into all the mechanisms here, but I won't, because again, it'll just be kind of a lengthy process. So now that we've covered 10 different reactions, right, it's a lot of reactions to go over, and again, that's partially why I didn't want to go over all the mechanisms, because it just takes so much time. We're going to go through and talk about kind of all the different examples so far of reactions and try to do some synthesis work and figuring out what we need to do in order to form certain products, okay? So we have some examples here on the next page, but I'll give some more too as we're going through, because it'll be kind of closely related to what the homework is involved with, right, with doing these synthetic problems.